Hello everyone, welcome back to my channel, and in this opportunity I want to present to you about how we can simulate the uh, pipe with the double elbows, and there is a crude oil or benzene flow inside it with the 600 psi in the inlet, and we're gonna see or we're gonna determine what is the decreasing or the deviation of the pressure from the inlet to outlet. Let's get started. Okay, and just follow my explanation, and don't forget to like, subscribe, and comment after you watch the video tutorial. Let's check it out. Okay, first of all, we open the ansys workbench and look at the left side of the window. We select the fluent and drag it into the green box in the center until it turns red. To create the standalone system, we release it. And then we change the properties. Just click the geometry, point number 2. In the analysis type, in the right side of the window, we change from 3D into 2D. Okay, before we start to print any geometry, we save our file first. Just click File, Save As, and choose our destination folder. And then we put a name on it. I will put 2D elbow pipe. And then click Save. Okay, that's very simple. Alright, just wait for a few seconds to terminate it. And after that, we right click the geometry, point number 2 again, and then select the new design model geometry to create our geometry. And wait until the design model window to open. Just wait for a few seconds. Okay, after the design model window has been opened, we select the XY plane with 3 outline, and then we look at the XY plane, choose the Z-axis, click the Z-axis and the UCS. Okay, and now we change our units first, which is in the default, it is meter. We change it into millimeter. And then we switch the tab from modeling into sketching. In draw, click line. We could simply create the line by clicking the center of the axis in the canvas, and then drag to the right for the first horizontal line. And then we change the dimensions right here by clicking the general. Just put it in general, click the line, drag it to the bottom, and then we change the first dimension into 2000. Okay, look at it. We click zoom to fit, or we click mannequin to zoom to fit, or to zoom in, or zoom out. Just simply click the zoom button, and then we drag it to zoom out. Turn it off. We draw again line. Click to the point right here, and then we create a vertical line right here. Right, and then we draw the third line, which is the second horizontal line. Okay, we put the dimension again, the vertical line and the horizontal line. In the details view, we change the vertical line into 1000, and we change the third line, the second horizontal line, into 1500. Now we are ready to have 3 lines right here, and we will create an elbow. Just simply click modify, click fillet, The radius, change it into 100. We click the first line, and then we click the second line. And also we click the second line, and we click the third line. Now we have a fillet right here. To create a pipe, in the modify we choose offset and hold the control button in the keyboard, and then select the first line, the first fillet, the second line, the second fillet, and the third line, and then right click in the line and end selection. Now we place offset into our destination right here. Just put offset as you want it. Okay. Now we got our pipe right here. Alright. And the next things to do, creating the line as our inlet and our outlet. Just we go back in the draw, click line. If we want to zoom in, perhaps it is not clearly viewed. We just click the button of the bottom and just we zoom into our destination, and then we draw the line for inlet in this section. Okay, done. Send to fit. Okay. We draw a line in this section to this section. The line is not proper, just simply draw a line from here to here. And then we, in the modify, we select trim to cut off the line. Okay. Send to fit. And now to make sure the diameter of the pipe is according into our desire, so we go back to dimensions, click general, and then we click the first line, the inlet line, drag it to the left. In the details view we change it into 100. Okay, this seems to fit. 100 is too big, so we change it into 65. Okay. Alright, I think it's fit into the pipe right here. And now what we're gonna do is we create the surface from this sketch. First, from the sketching tab we switch into modeling tab, and then we select our sketch one, and then we click the concept and click surfaces from sketch. Okay, in the best object in the details view window we click apply, because it is automatically selected as it is colored by yellow for our sketch, and then click apply, and then click generate. Now we've done our modeling for our geometry right here, and to define and to create our meshing, we must switch our window into a meshing window, and don't forget to save it first. Just click save project. Just wait for a few seconds. Okay, and then we minimize this window. We go into the mesh. We just click the mesh, and then we right click into edit and wait until the meshing window has been opened. Okay, after the meshing window has been opened in ansys fluent, we click the mesh and we generate the mesh first to look at what is exactly our mesh gonna be. Okay, just wait for a few seconds until the meshing is done. Okay, now as we can see right here, our meshing is quite rough enough, so we're gonna smooth it. A little bit. So we're going to make a smaller mesh. Just simply change the element size in the details of mesh in the bottom left corner of the window. In the element size, change it from default. So by default it is 182.92 millimeters. We change it into 20 millimeters. Click enter. And then we regenerate the mesh. We just wait for a few seconds until the meshing is done. Our meshing is done right here, right now. We still have very rough meshing right here. So we change the element size once more into 5 millimeters. We click again the mesh and we generate the mesh. Just wait for a few seconds until the meshing is done. After our meshing is done, now if we want to check our mesh quality, we can do some of testings or checking. Now I will teach you how to determine the mesh quality. Actually, we can see from many sites, but mostly people determine the mesh quality from the two things, which are the aspect ratio and the skewness. Simply in the details of mesh window in the display style, let's get started with the aspect ratio. Okay, change from use geometry setting into aspect ratio. So what is exactly the aspect ratio? The aspect ratio is the ratio of longest edge length to shortest edge length. It should be equal to 1 for an ideal mesh. As we can see in here in the legend, the approaching values to the 1 is colored by blue, and the highest value is colored in red, which means that the blue color mesh right here, or the blue color shell, is represented as represents as the best mesh, and the red one is the worst mesh. So it is less important in the boundary layer mesh. Okay. Now, if we want to look into the mesh, we can zoom in into the mesh. Okay. Right. As we can see in here, mostly the mesh has been colored in blue, which means that we have so many very good mesh. Okay. The second style we can use to determine our mesh quality is the skewness. In the display style, in the details of mesh, change the aspect ratio to skewness. Okay. Now, what is exactly skewness is? As we can see in the screen, value of 0 indicates an equilateral shell. Okay, it is colored in blue, which means that it is the best mesh or shell that we have it. And a value of 1 or closest to 1 indicates a completely degenerate shell or worse shell. Highly skewed faces and shells are unacceptable because the equations being solved assume that the shells are relatively equilateral or equiangular. You can also see to zoom in the mesh right here if we want to. Okay, so we can see in here mostly our meshes are blue, which is that our mesh is okay to go, and we are ready to transfer it into the solution. Okay, before we transfer it into the solution, first we must create our boundary condition or our boundaries. First we select the line first. Okay, we we start from the inlet. We select the inlet right here, right click, and then create name selection. We create it as our inlet. Okay, click OK, and we create our outlet as this line. Okay, right click in this line, create a name selection, and we rename it as outlet. Okay, all right, and we click the rest of the lines. Click Control, then Control in the keyboard button, and we select the rest of the lines. Right click, create a name selection. We rename it as wall. Click OK. Okay, after we're done, if we want to recheck our name selection for our boundary, we can click in the outline window, click name selection, click one of them, one by one. Okay. Now we are ready to transfer this into our Fluent solution. How to do that? Just right click in the mesh in the outline window, and then we click update until you got an information from the Fluent that our file has been ready, transferred or translated into Fluent. Okay, after that we click the file and we click close meshing. Now we have done our meshing right here, and we go back into the workbench window. In the setup, we click setup, and then we right click the setup and then click edit until our setup window has been opened. Just wait for a few seconds. Okay, now the Fluent launcher window has been opened. We click the double precision right here, and then we just leave the rest like it was, and then we click start. Wait for a few seconds until our solution window has been opened. After the solution window has been opened, in the task page we let the time in steady, not transient. The solver type is pressure based, the static P in the general, and then we double click in models. We choose viscose, double click in viscose, and then we change the model into K epsilon, the K epsilon model in realizable, and the near wall treatment we choose enhanced wall treatment, and then we click OK. Okay, now we turn into the materials, double click in materials, we double click in fluids. So we will create or edit materials. So we open the Fluent database first, and then we choose our materials in benzene. We look at the benzene. Okay, benzene liquid. We choose benzene liquid, and then click copy and close. And then we click change or create, click close. Now we select benzene liquid as our materials. Okay. Now we turn into cells and conditions. Double click it. Click in the surface body. Click edit. We change from the default air into benzene liquid, the material that we have selected before. Click OK. Okay, and then we turn into the boundary conditions. Double click in boundary conditions. We select inlet. Now in the type we choose pressure inlet. Okay, before we define our pressure inlet, we change the units first. The units, just click the units. We select the quantities in pressure, and we change the unit from Pascal into PSI. Okay, click close. We go back to the task page again. In the inlet, we select the type into pressure inlet, and then we click edit. And in the gauge total pressure, we change it into 600 psi. Let the rest of it just let it be, and then click OK. And then we click the outlet. Just let the type into the pressure outlet. Click edit. Okay. Now we just select the gauge pressure into 0 psi in the outlet, and then click OK. And we're gonna see the wall specification. Click edit. Okay. Nothing at all right here to be changed. Okay. Now we have finished to define our boundary conditions. We go into the solution. We click method, double click methods. Change the shade from coupled into simple. Gradient into green gold cell based. And we change the turbulent kinetic energy because we want our results to be much more accurate. We change it into second order upwind. Okay, and then now we turn into controls. Just let it be like this. Now we go into the monitors, expand the monitors, double click residual. Okay, in the absolute criteria, to get our result much more accurate, we change it into 1 E minus 6, which means the absolute criteria will be in the value of 0.000001. We copy it into all of the equations, epsilon k, y velocity, x velocity, continuity, all of this. Okay, click OK. Alright. Now we go into initialization. Double click initialization. In the initialization methods, we choose in the standard initialization, compute from inlet. Okay, we click initialize and we wait for a few seconds to be initialized by the fluent. Okay, after we done our initialization, we go directly into run calculation. We run our calculation, double click in the run calculation, and we input the number of iterations for 5000. Okay, now we are ready to run our iterations right here. All of the setting has been done, and then we just click calculate. Okay, just let the ansys fluent to iterate the simulations, and the ansys fluent will open the residual plot in the window, in the solution window, and we can monitor the graph or the chart of the iteration itself. We can also monitor the percentage of the iteration later. Okay, now we can see the scale residuals graph right here is moving, and also in the console we can see the iteration is going on, and we can also see the percentage of the iteration right here in the bottom right corner of the window, and we can also stop anytime we want to stop the iterations. And as we said before, that our number of iterations will be 5000, so we just wait until the iterations is over. And in the bottom left corner of the window, we can also see the iterations remaining. So we're just gonna wait for a few minutes, or maybe 15 or 20 minutes to be finished until the simulation or the iteration is converged. Now, after we got our calculation is complete and our iteration has been converged, click OK in the information, and if we want to look at the results, we perhaps want to see the counters of the pressure. We can click the graphics in the counters, and then we can rename our counter name as we wanted. Perhaps we want to rename it as counter pressure counter. Okay, pressure counter 1. Okay, in the options, just let it field, node values, boundary values. Just let it be like this, and then in the counters of pressure, which is pressure, and in the sub counters of, we choose total pressure, and in the surfaces we select all of the surfaces, and then we just click save display. Okay, now in the counters of total pressure in the display window, we can see exactly what is the result of the picture right here. In the legend, we can see that the blue color represents the lowest pressure right here, and the red one represented the highest value of total pressure. And as we can see in here, we can also zoom in. Click zoom in. We can zoom in right here. As we can see in here, near in the elbow, we have almost we have the lowest pressure value in here. Okay, right in the elbow. You can also drag the picture. Okay, and in the inlet, we can see that the color here near the inlet is completely red, almost the entire zone right here. But near the outlet, the color is gradually changed. It is changed significantly until in the outlet it is mostly orange, yellow, and green. It means that there is a degradation of, or there is a decreasing of the pressure itself. Okay, we can also see. Just click close. We will create another counter. Double click counter. We rename the counter name. We rename it with the pressure counter 2. I want to see the static pressure. Select the entire surfaces. Click save display. Okay. Now we can see in here, we can see clearly that in the elbow section, right here, elbow section 1 and 2, exactly at the inside elbow, there is the decreasing of the pressure. It is almost blue right here. It's almost all blue right here, but mostly still yellow and green. But there is some particular section which is blue right here. Okay. Now in the next counter, double click again. I want to see the velocity counter. I just want to see how or why this section in the inside elbow is decreasing about the pressure, why the pressure is decreasing right here. I want to see what is the relationship between the decreasing of the pressure with the velocity itself. Okay, I'm going to rename the counter name into velocity counter. Okay, the counter solve, we change it into velocity. Sub counter solve, let it be in velocity magnitude. Select all of the surfaces, click save or display. Voila. Now we can see right here in the elbow side, especially in the inside of the elbow, the color is nearly orange and red, most of it. Okay, and the outside elbow is green, both of it. Okay, so which means that there is the increasing of velocity in this section, in the inside of the elbow, both of the elbows, which means that the relationship of the velocity with pressure, that the increasing of the velocity will affect the decreasing of the pressure itself in the inside section of the elbow, both of the elbows. Okay, that is the analysis of the pressure, or the relationship between the pressure and the velocity. And we can also see the factors of the velocity. Double click in the result, double click factors. We rename the vector name into velocity vector 1, and we can choose the vector, so just let it be in velocity, colored by, I want to be colored as the pressure, static pressure. Just select all of the surfaces. The style of the arrow, I will change it into the field arrow. The scale, I just want to change the scale into smaller, 0.2. Click save and display. Okay, as we can see in here, there is a decreasing of pressure right here in the inside of the section elbow. Okay, remember the color is based on the static pressure. Now I want to create another vectors. Rename the vector name the velocity vector 2, and now it will be colored by the velocity itself. Just like velocity, and fill all the surfaces, fill arrow, change the scale to 0.2. Okay, save and display. Now as we can see before, there is increasing of the velocity in the inside section of the elbow. Right. Okay. And okay. Alright. That is our analysis based on the counters and vectors in the fluent. And now for the decreasing of the pressure, we can also analyze or determine how many the delta pressures between the inlet and the outlet. In the result reports, we click the surface integrals, double click surface integrals. In the report type, we change it into phase average, and in the field variable, we just let be pressure. In the subfield variable, we change it into total pressure, and we just click inlet and outlet because we want to determine what is the difference between the inlet pressure and the outlet pressure. How many the delta pressure between the inlet and the outlet. Just okay. After that, just click compute. Click close. If we want to see the result, we put back the console, double click the console. Okay, now we have in here that in the inlet we have 600 psi, and in the outlet we unfortunately we have the decreasing of the pressure until 418 psi, which means that the pressure from the inlet is decreasing around 200 psi. Okay, so the delta of the pressure between the inlet and outlet is around 200 psi. Okay, that's all for the simulation of the ansys fluent for double elbows pipe in 2D type, two-dimensional type of analysis in fluent. And we can see many things right here, from counters, vectors, and also the deviation or the decreasing of the pressure from the inlet to outlet. And we can still do many more for the analysis in fluent. So don't forget to like, subscribe, and comment into my channel. Okay, thank you very much. That's all. Thank you very much.